Okay. We just got done summarizing class 17, and we have our two reactions here, reaction 17A and 17B. The second class in module 7 is class 18. I just want to try to memorize my color coding. Okay, I think I got it. Class 18, still module 7. You should be looking at your handout because you need to be able to do this on your own eventually. I can't be making your study sheets all the time. Reaction 18A. I like to give a title to each of my reactions. It helps me remember and recall information because the title is sometimes very descriptive. Look at this title, non-Markovnikov. I know what that means. Let's do the opposite of what you were taught. Non-Markovnikov addition. So we learned the addition reactions with the alkenes, but what are we adding in this case? HBr. Can I use HCl? No, it says not to use HCl, HBr. And I'll put here HBr only, not HCl. Sometimes I forget. Okay, we're going to start out with some examples. We're going to leave the product blank, and I'll give you a chance to draw the product. Non-Markovnikov. Okay, so let's try this one here. Non-Markovnikov addition HBr needs HBr, obviously. But if we did that only, it would be Markovnikov. That's exam 2. To switch it over to the radical mechanism and the non-Markovnikov addition, we use peroxide. So here I'll use methyl peroxide. Don't forget, as a trick, each carbon gets something. Okay, we've seen this before. But now, instead of bromine going on the more substituted, we're going to put bromine on the less substituted. Is there any example that's a little bit harder than this? Not really. So we'll just have one example. But there are a lot of points about this, especially for the stereochemistry. First thing is, do not need to know the mechanism. But it's very useful to know the intermediate. But it's useful to know bromine adds first to make more stable radical. Your radicals go stability from tertiary to secondary to primary. That's super important. Also, so the bromine adds first, that means the hydrogen adds second. The bromine adds first to form a radical. For stereochemistry, you should know that a double bond is flat. So our starter material is flat around the double bond. The double bond, let's say, let me write this over. It's you remember in lab we counted the number of atoms that are in the same plane. It's this one, this one, this one, this one, this one, and hydrogen. It's really the atoms around the carbon-carbon double bond. So let me write that. 6 atoms around double bond, flat. What that means is that when the bromine adds, it's going to add from the front and from the back. Wedge and dash. And we're recording here, Caitlin. Please excuse the interruption. But also your radical is sp2 hybridized, so that's also flat. So we're going to have wedge and dash possibility. All right. The product. The product looks like this. Your bromine is on the less substituted carbon. Okay. If you want to do if you wanted to do this idea that you have an intermediate, let me underline it. What does that look like? Is it possible to have this question? Maybe. You should know what it looks like because it helps determine that this is non-Markovnikov, meaning that the bromine adds first to make the more stable tertiary, in this case, radical. And that's why it's non-Markovnikov, because in the Markovnikov, the hydrogen added first to form the more stable carbocation, and that's why the bromine would go here if this was if we went through the carbocation. But this is we go through the radical, it's actually the bromine that adds first, and then the hydrogen goes on. Now, this one's a simple case because we only have one chiral carbon. So is it true that the bromine came wedge and dash? I wrote it here that the bromine adds to the flat double bond. So yes, you do have wedge and dash and it's racemic. But just on that chiral carbon. So your two stereoisomers are this. The simplest way to draw it is wedge and dash. So I mentioned that I couldn't think of a harder example. There is a harder example. The harder example is if I had two chiral carbons. So let me give you that example. I'm not going to work it out all the way for you. How do we get two chiral carbons? How about this? Well, I can't leave it like that because the double bond carbon on the left would have two hydrogens, so that wouldn't be chiral. I need both carbons to end up being chiral. And so, dang it. Let's try this. If we use HBr, and you could also use hydrogen peroxide as a peroxide, you could pause the video and see if you could get the products here. The one product without stereochemistry, and then we'll determine whether we have one or two chiral carbons. I really hope we have two chiral carbons. So the bromine goes here. The hydrogen went on this carbon, which was a tertiary radical, and this is what I wanted. Chiral there, chiral there. So ultimately, and I'm not going to draw it here for you, you have 4 stereoisomers. One of them is this. You don't have to draw the hydrogen. By making this wedge, you imply that the hydrogen came in dash. By making this, let's say wedge also, you imply that the bromine came from the front. So there are 3 more after this, okay? Plus 3 more stereoisomers. All right, you're gonna do that on your own. That is, in my mind, this is complete. It doesn't have everything. Like I'm looking at the handout, but it has, it pretty much has everything. So that's reaction 18A. Any questions about this reaction? No questions? Let me just underline, I think some people are not understanding this. when you add the bromine or the hydrogen, you're adding it to a carbon that has trigonal planar geometry. The double bond is trigonal planar, and also the radical is trigonal planar. And so that's the last thing I'm going to write here. When you have these two flat portions, both are trigonal planar. And so when you add that fourth group, potentially you could have a tetrahedral carbon that has four different things, which would be chiral. And when you add to a trigonal planar carbon, it's flat. So there's equal probability that you could go on either side, 50-50. All right. Again, you should be looking at your notes. Make sure you don't miss anything. Okay? Okay. Reaction 18B. Let's do that real quick. I'll say it here. I said in the previous video that this is different than the roadmap. Some people like the roadmap, some people like lists. Honestly, I like lists when I'm first learning the reactions, but if I'm trying to put all of these reactions together in a synthesis, it's the roadmap that helps me the most. And so I use both. When I first start to study, I study the lists, right? I study the lists. But then when I figure out, oh, there is a way to go from alkane to alkene to alkyne, I take the individual reactions in the list and I then put them together in a roadmap to see what's the fastest, most efficient route. Okay, enough talking. Reaction 18B. It is called beta hydrogen elimination. I understand that it's in the module radicals, but it's not a radical mechanism. Did people realize that? This is not radical. So, let me space this out a little bit better. Nope. Okay. Not a radical reaction. So why are we talking about this in this class? Because we made a bunch of alkyl halides, not only here for 18A, but we definitely made alkyl halides in reaction 17A. 17A. So what can we do with our alkyl halides is we could eliminate. And that's why I put it in this chapter or this class. Again, we're going to start out with overall reactions. Heck, let's use this one, this alkyl halide here. Br. That's an interesting one. To do beta hydrogen elimination, you need a strong base. My favorite base is NaOET. And that's it. Oh, this one is new. So if you're bored by this, sometimes the solvent is added also, ETOH. I mentioned this in one of the ACE problem sets in the answer key, not in a video, but on PDF. Let me talk about this on video. These two are very similar, these two, okay? This one here on top, is the anion. So we have this, O minus. But this one at the bottom is neutral, HO, okay? So who's going to be the eliminator? Who's going to be the base? When you have a negative and a neutral of the same type of molecule, this is the winner. So I'm going to say this is the base, and this is acting as a solvent. It really does nothing except dissolve. So when you draw the mechanism, you are using for sure this, the O minus. Okay? Okay, I haven't been putting a lot of solvent in my reactions, but the textbook is starting to put solvent, especially when we do substitution and elimination together. Let's focus on elimination. It's beta hydrogen. So not only are you eliminating the bromine, you are eliminating a hydrogen on each of these beta carbons. Okay. Okay. In the notes, we're going to put here, know the mechanism. This study sheet is, and this video is not to go over the mechanisms. It says here to go over the mechanism on your own. So you'll have another blank sheet of paper, and you'll be doing a lot of mechanisms over and over again, okay, until they're automatic. This is just jotting down all the points that you want to remember to study. Is there anything else? Okay, how about this? You'll form an alkene. No, even before that. You use a strong base, right? Use a strong base. Those are your O minuses. HO minus, RO minus, even the N's. NH2 minus, or RNH minus, or R2N minus, like LDA. If you don't know any of these, or if you got lost in this list, go back to this class. I listed strong bases at the bottom of page 2, right? Page 2. Okay, next. You form an alkene. Form an alkene. And the double bond is between the alpha and beta. All right, so let's draw the products. Maybe there are a lot. Maybe. So our first product, draw the double bond to the left. You're getting rid of the bromine and the hydrogen to its left. If you want to label 1 and 2, beta 1, beta 2, this is alpha, this is beta 1. You may notice that this is what? This is trans. How do I know this is trans? Or you could even say it's E, right? The priority here is up, the priority here is down. That's opposite. Let's use E instead of cis and trans. Let's use E and Z. This is E. Well, if you could draw E, Z is possible. You know why Z is possible? Because you could rotate, it's a little sloppy, but you could rotate this bond right here to get the ethyl down and the methyl up. To get the ethyl down and the methyl up. So some percentage is going to look like this. The methyl up and the ethyl down. That is Z. So in exam 2, when I was testing you, can you convert E to Z? That's especially useful now, this skill. Let me redraw this carefully. Now you could get from E to Z very, very quickly. It is still between alpha and beta 1. The other alkene, if you form it to the right, let's form it to the right now. That's neither. So we are not drawing the stereoisomer. There is no other stereoisomer with a double bond on the right. This is neither. Okay? With this beta hydrogen elimination, 4th bullet point, Zaitsev. Zaitsev said the more stable alkene in a mixture is the major product. Do we have a clear winner for these 3? It's not going to be this. Okay. We had practice on this, right? Did we have practice with mono, di, tri, and tetra? We had it practice here. Do you see this? We circled the tri-substituted, more stable than the di. If you're still having trouble with that, you really have to find an SI or me. Because now I need to know who's the more stable of these 3. You should know that this is mono. Because the trick, I don't know. I don't like this trick, but it seems to work for other people. you have 3 hydrogens. Every double bond has 4 positions. So if 3 are hydrogens, 1 is a substituent. I don't think that's a great trick, but people like it. So these 2 are tri-substituted. Oops. These 2 are tri-substituted. Who has more bumping? Who has more strain? Do you see how these 2 bigger groups, the ethyl and the methyl, the ethyl is bumping the methyl, but here the ethyl is bumping the hydrogen, which is less stressful. Hydrogen is small, so the ethyl bumping hydrogen is less stressed out than the ethyl. Oh, you don't see what I'm pointing at. The ethyl bumping into the hydrogen is less stressful than the ethyl bumping into the methyl. You see, methyl is bigger than hydrogen, so the bumping is worse here. Tricky. Tri-substituted, and you have, we call this the trans. So here E, or, so I guess using trans and cis is useful because, do you remember, cis and trans is dependent on size. E and Z is dependent on priorities. So maybe it is good to use cis and trans. Trans is usually more stable than cis. Okay. Let me double check. Is there anything else for that reaction, 18B, that I forgot? Nope. Okay, so let me clear this up one more bit. Any questions about 18B? All right. In this review session, again, look what we have. Those who came on time and did not interrupt me in the middle of it. We have class 17, 2 reactions. That's the first video from today. And then when we just did class 18, 2 reactions as well. We got everything that we need on 2 pages. Everything except for the mechanism. But really the mechanism is just you finding 3 or 4 blank sheets of paper and drawing it. Which mechanism do we need to know? This one here. And drawing it 3 or 4 times. Honestly, this is the only mechanism you need to know from the first 2 classes after the exam 2. This one right here. Okay. The other ones, you just need to know the intermediates. All right, class 18. Any questions about class 18? We're gonna stop here, but what's the next step for you all? If you like the lists, do one for class 19. Do one for class 20. Once you're done with the lists, try the ACE. Try it. Do you think the ACE is easier with this in front of you? Okay. And then eventually you need to know how to draw your own study sheets, whether it's going to be roadmaps or lists or note cards. You could use these, okay? This is fine, but it's not going to be as helpful as you trying to struggle with your handouts and trying to kind of organize everything or the important parts. You pick out the important parts. After you do the ACE, then you do stuff like synthesis, and then you clean up everything. You do the mechanisms faster, more accurately, and then you do what? You read through the handouts to make sure you get all the multiple choice. All right, so there's always a kind of a strategy, but you have to find what works for you the best. Okay. Man, those are very, very pretty.